Okay, guys, welcome. It's Mrs. Webb here again with you guys. And today we're going to start our acid base unit. So last unit in Chemistry 20. And kind of exciting because this is really where, we get into the meat of the chemistry course. The stuff that you guys are learning is stuff that you'll, definitely make use of moving forward. So it's kind of exciting for you guys to be at this point. So with the acid base unit, we're going to continue on with talking about Arrhenius. The only thing we're going to do now is we're going to modify a little bit how we define our acids, bases, and our neutral substances. So just to kind of give you an idea of where you guys are going to be going. Prior to our solutions portion of the unit, you guys have been learning here at this level, talking about empirical properties of acids, bases, and neutral substances. And when we talk empirical properties, we're talking about those observable qualities that we can make qualitative observations on, right? So we know acids taste sour, bases are slippery, things like that. We just finished looking at a unit where we talked about Arrhenius, and we showed how Arrhenius defined acids as solutions or substances that ionized in water in order to produce hydrogen ion, and bases were ionic hydroxides that dissociated in water to produce hydroxide in ion in water. And everything else, according to Arrhenius at this point, everything else was a neutral substance. Now, you guys did your inquiry lab where you looked at a bunch of different solutions and you predicted whether they were acid, base, or neutral. And you notice that a lot of those neutral substances that you predicted were indeed not neutral. They tested acidic or they tested basic. And so that's essentially what Arrhenius also realized. And that's what's going to move us here into level 3, where Arrhenius had to modify his original definition in order to explain why those solutions were testing acidic or testing basic, even though they didn't have a hydrogen ion or a hydroxide ion in the chemical formula necessarily. The other thing also that Arrhenius's original definition didn't explain was why some acids were stronger than other acids and why some bases were stronger than other bases. And so this modified Arrhenius also includes that. That's basically where Chem 20 leaves off. Moving forward, you guys will have a look at Bronsted-Lowry in the Chem 30 curriculum. And then the next level up will be Lewis. So those are kind of the solutions gurus moving forward. Okay. So just there's a little bit of kind of interest stuff here for you guys about acids and bases, where the names come from. I'm not going to spend too much time on this because this is really just for interest's sake, so that you know a little bit about where the term acid, where the term base comes from. I've listed here for you guys some common acids that you guys would find in regular consumer products, right? So citric acid in fruits, lactic acid in sour milk, vinegar we've talked a lot about. And then here are some common bases for you guys as well, so that you can see where bases are used in everyday life, because they really are used quite a lot. Now, going back to that level 1, here are the empirical properties that you guys need to understand and know. I feel like at this point they're probably something you already have in your head. But with acids, we know they taste bitter, This is one that students tend to forget, but acids react with active metals to produce hydrogen gas. So remember, if you put magnesium metal, like that magnesium strip that we did in the lab, if we put that with an acid, hydrochloric acid, we produce hydrogen gas. Litmus paper turns blue litmus to red. Acids neutralize bases. Acids are conductive, and they have a pH less than 7. We're also going to talk about pH this unit. Bases taste bitter. They feel slippery. They turn red litmus paper to blue. Bases will neutralize acids. They are also conductive, and bases have a pH above 7. Okay, so those are all the empirical properties that you guys are required to know. The level 2, that's our Arrhenius level. So just a quick recap of what we talked about last unit. Remember that we defined our acids as any molecular compounds that had an H at the front or a COOH at the back. And we said that those molecular compounds, specifically, what they did was they ionize. So that was a term that we introduced last unit, and we talked about ionization reactions. And a typical ionization reaction was something like this. If we have hydrogen chloride gas in solution, we put it into solution. So we put that into our water. That's going to ionize. And at this point, we didn't explain what exactly was happening. We just said something happened when we bubbled that hydrogen chloride into the water that made hydrogen become charged, right? So it gave hydrogen a positive charge, and then the chlorine developed a negative charge. Now this specifically was what Arrhenius said gave acids their acidic properties. If we wanted to have, all of those empirical observations, we had to have hydrogen ions floating in solution. Bases we said were metal hydroxide that dissociate, okay, because they're ionic. So bases dissociated to produce OH negative. And so if we took something like sodium hydroxide, we placed it in our water, this would dissociate into sodium ion and hydroxide ion. And again, according to Arrhenius, it was the hydroxide ion, that was the definition of our Arrhenius base. It was that hydroxide ion that gave the solution its basic characteristics. It made it feel slippery. It gave it a pH greater than 7. All of our other substances, according to our previous definition, or Arrhenius's previous definition, all of our other substances were neutral in water. Okay, and something else that I want to define for you guys is when we talk about this hydrogen ion, this acid ion, we've referred to it as the hydrogen ion, H plus aqueous. But the other thing I want you guys to realize is that if hydrogen has a positive charge, that means that hydrogen has lost one electron, right? Its only valence electron. And so really, a hydrogen ion is just a proton. It's a single proton. So a lot of times people will refer to the hydrogen ion as a proton because it really is just a proton floating around in our solution, right? The thing with your proton is that a proton, if you think about just one single proton in the middle of the nucleus, a proton is very, very small. And it has, the positive charge that is exposed to water. So what happens? Because at this point, the reason I'm bringing up the proton is that Arrhenius started to realize that we can get some acids that are very, very dangerous, right? They're really quite horrible substances, right? They're extremely corrosive, things like that. They'll burn holes through your clothes and your skin and stuff like that, right? We always want to be careful when we deal with acids. Things like battery acid, terrible stuff. And so what Arrhenius started realizing was that if hydrogen ion really is just a single positive proton floating around in water, and it is really so small, it seems kind of unlikely that this one proton floating around in solution, and I mean, I'm saying one proton, but you know, obviously there's definitely more than just the one proton, but it seems weird that such a small little thing could have such a such an impactful such a strong influence on a solution to make it so corrosive, for example, like battery acid. And so what Arrhenius started doing is he started thinking about, well, what could potentially be happening that would give something or a solution these properties that could be so damaging, that was maybe perhaps a little bit bigger than just a proton, because it did seem a little bit unlikely that a proton could have so much power over these empirical properties of solution. And what he came up with was, we have this single proton here floating in our solution. Here's all of our water molecules. And again, remember that water also is has a polarity attached to it. So the negative end of these water molecules is going to be attracted to this positive proton. And what he realized was that more likely what was taking place was that there was an actual reaction between this proton and the water molecules. And this is what he called protonation of water. And so that's something that you should remember, protonation of water. And what was happening when this took place was your hydrogen ion that was in solution reacted with your water molecule, and the hydrogen ion actually attached itself to the water molecule and produced what we call H3O+. This is what we call the hydronium ion. Oops, let's grab a pencil here, or a pen. This is your hydronium ion. And Arrhenius realized that this hydronium ion, it was much more likely that something like this could have such a profound effect on a solution in comparison to the hydrogen ion. And this was really the basis of all of his level 3, his modified Arrhenius revelations. Because what he realized was that the water wasn't just this, passive participant that just dissolved or dissociated or ionized. The water was actually actively engaged in the solution, and there were reactions that were taking place with the water. This one being the first one in order to create hydronium. And so that's kind of the first big difference, is that now Arrhenius modified his definition to say that it wasn't this hydrogen ion or this proton that's giving acids its acidic properties. It was actually this hydronium ion. So from here on in, we're going to talk about the hydronium ion versus the hydrogen ion. Now we're going to redefine our definition to specifically talk about acids forming hydronium. Okay, and if ever there's a question to ask you specifically about hydrogen ion, it'll specify in Arrhenius's original definition, so that from here on in you can assume that we're referring to hydronium ion because of that protonation of water. So that was the first kind of thing that Arrhenius noticed, or that Arrhenius realized, was that the proton seemed really small. It was highly unlikely to have such a big influence on solution, protonation of water, forming hydronium. Bam! This is what causes acids to have their empirical properties. Now, the next thing that Arrhenius noticed, much like you guys noticed when you did your lab, was that according to Arrhenius's original definition, acids were molecules that had hydrogen in the front or a COOH in the back. Bases were substances that were ionic hydroxides, and everything else was neutral. But what Arrhenius's definition, his previous definition, couldn't explain was why compounds like, remember, carbonated water, why compounds like carbonated water tested slightly acidic instead of neutral. Because if we look at the molecular formula for carbon dioxide, there is absolutely no hydrogen in there. But you guys tested it and you saw that it did test slightly acidic. The same thing happened with many other solutions. The other thing, as I alluded to earlier, was that it couldn't differentiate, his original definition couldn't differentiate between a strong versus a weak acid or a strong versus a weak base, right? And so this is where he started revamping his definition. And what he talked about again was that water wasn't that passive participant. Water actually was actively engaged in these solutions, and there was a reaction that was taking place with the water that we call hydrolysis reactions. Hydrolysis meaning water breaking. Okay. And the two hydrolysis reactions that are important for us are the acid hydrolysis reaction, in which you have your solute reacting with your water. So remember, in original Arrhenius, we didn't actually have a reaction with water. The water was just something that sat on top of our arrow, indicating that we were replacing our solute in water. Now there's an actual reaction. You're taking your solute, it's reacting with the water. It's going to produce hydronium instead of hydrogen ion. And it's going to produce a solute anion, which we also call a conjugate base. For the base, in order for, or modification for the base, is we actually have a solute anion. It's going to react with water, and that's where the base is going to produce its hydroxide ion plus your solute, which is your conjugate acid. And here's the big thing. With modified Arrhenius, essentially, if we want to produce hydronium, that water molecule is going to gain a hydrogen to produce hydronium and the acid. If water is going to produce a base, it's going to lose a hydrogen ion to produce hydroxide. Because remember, water is HOH. And so if it loses a hydrogen, it's going to produce OH minus. So that's where the base appears. Okay, so that's the first thing. The next thing is our definition of our strong acids. So here I've got an example of a strong acid. And remember, we talked in class about how strong acids are all those acids that are above the gray line in your acid base, in your acid table. Right on page 8 and 9. So there's 6 of them. Nitric acid, HNO3, that's one of them. And so now, instead of undergoing ionization, nitric acid undergoes a hydrolysis reaction, and it reacts with the water. In that reaction, the hydrogen is donated to the water, which produces hydronium ion. And then the nitrate is left by itself, NO3 minus. So that's your conjugate base, your solute that's produced. This is officially that brand new modified Arrhenius reaction for your acid. In this case, the hydrogen goes over to the water, produces hydronium, and then you're left with NO3 minus. Minus, just one minus, because this HNO3 lost one proton, so it becomes 1 time more negative. The other thing is, because it is a strong acid, on top of this arrow, we now place 100%. You may see sometimes that people use greater than 99%. Greater than 99%, 100% are kind of used interchangeably depending on where you, what class you're in. We'll just use 100%, but just be cognizant of the fact you might see greater than 99% as well. This 100% over top of the arrow, that's the proof that this is your strong acid. So a lot of times you'll have to prove that this is a strong acid. That right there is your proof. It's not a paragraph or anything like that. It's just writing that 100% up there. And the fact that this is going to test acidic, if you're proving that it tests acidic, you're going to show that hydronium is being produced. So that's your proof of acid. Whenever it says prove something, you're not writing a paragraph, you're writing these hydrolysis reactions to show the strength of the acid or the base and the production of hydronium or hydroxide. So that's for a strong acid. For a weak acid, any of the compounds that are below the gray line, a weak acid, when you place it into water, it still undergoes hydrolysis. The thing with the weak acid is that less than 50%, and it's always less than 50%, less than 50% of that particular substance will undergo hydrolysis. So if we take our CH3COOH, our acetic acid, it's going to undergo hydrolysis. This final hydrogen is going to be donated to the water to produce hydronium. And then what's left over is your CH3COO minus. Now, here's your proof of acid, right? You're producing hydronium. And then this is your proof of weak acid, that only less than 50% is going to react. And we use these equilibrium arrows when we write a weak reaction. So let me show you, I want to just draw one thing. I've got it later on so that you know, or so that you can visualize this. If we put this into our beaker, here's our water, and we're going to bubble in our HCl. The thing with your HCl is that 100% of it, the entire thing, all of what goes in there is going to be converted, or it'll undergo hydrolysis and produce hydronium ions and chloride ions. Everything that goes in there. The only thing we've got in there are ions. In the next example here, the big difference is that less than 50% of what goes in actually becomes ions. So yes, we're going to have H3O+. Yes, we're going to have acetate, CH3COO-. Okay, yeah, we've got both of those. But also in solution, we're going to have molecules of CH3COOH floating around in the solution. So not only do you have your ions floating in solution, but you also have, highlighter's not coming up, but you also have these ions floating in solution. And that's the big difference between a strong acid and a weak acid. In the strong acid, we don't have any molecules floating in solution. Everything became an ion. In the weak acid, we have ions, yes, but we also have these molecules floating in solution. Okay, so that's the big difference between strong and weak acids. Now, special acids, your non-metal oxides. That is your carbon dioxide, for example, or just your carbon dioxide. This is a separate example here. CO2, right? CO2, when we talk acidification of oceans, what actually acidifies the oceans is the carbon dioxide in the atmosphere that mixes with the water and becomes acidic. So here's what happens. There's two different ways you can show this reaction. This is the one I prefer because it shows you in 2 steps what's taking place. The textbook shows you the other. I'm going to stick with this one. You guys can use either or. They both end up with the same results. But essentially what takes place is you've got your CO2, right? Remember our carbonated water. We place it in the water. And remember that it's not just putting it into the water. Now there's a reaction that takes place. So The CO2 reacts with the water and it comes together and it forms generally a weak acid, H2CO3, aqueous. So this is just, we're clumping all of these atoms together to form a weak acid in solution. Generally, more often than not, it'll be a weak acid. H2CO3, because there's 3 oxygens there. Now, it's this H2CO3 that's going to undergo hydrolysis. So H2CO3 will react with your water. H2CO3 is not one of the acids listed above the gray line. So it's going to be a weak acid. So we use our equilibrium arrows and are less than 50%. The hydrogen from the H2CO3 is donated to the water to produce hydronium. And then we have HCO3 negative. Okay, so only one H because we donated the other H to the water, and a negative because, again, we donated our proton. So this is what happens with all of your non-metal oxides. And a non-metal oxide is always a non-metal that's attached to an oxygen. Okay, so whenever there's a non-metal oxide, in step 1, we're going to clump it together with water to produce typically a weak acid. And it may not be an acid that's on your acid table, but we'll treat it as a weak acid if it's not one of those top 6 acids. That weak acid will undergo hydrolysis and you'll get hydronium being produced. Okay, so that's your special acid that you have to remember. So what I recommend is that you keep yourself a cheat sheet or a study sheet or something that you have going with all of the things to keep in mind, because there's a lot of variables in this particular section. I wanted to show you this as well. So I already showed you this one, strong acid versus weak acid. What I wanted to look at here is the difference between a concentrated strong acid and a dilute strong acid. So if we look in this particular beaker, we don't see any molecules. It's just hydronium and some anion, but I'm calling the A anion. But there's no molecules in here. And if you look, the beaker's pretty full with ions. So this would be what we call a concentrated strong acid. The beaker down below is just ions as well, but there's only a very little amount of ions in solution. So this would be a dilute strong acid. Our bases, strong dilute acid, yeah. Our weak concentrated acid, if you notice here, we've got hydronium, yes, we've got anion, but we also have our molecule, our Ha molecule, HA, right? Here's our molecule, which means a weak acid. There's a lot of stuff happening in this beaker, so this is a concentrated acid, okay, even though it's weak. And in this case here, we have a dilute weak acid. So I know it's weak because here's my molecule, my Ha molecule, and then I have a hydronium and I have an anion. So this would be a weak dilute acid. Okay, and we're going to talk, I'm going to refer back to these diagrams, keep them in the back of your head. I'm going to refer back to these diagrams when we talk about pH as well. Now, we talked about the acids. I want to talk about the bases. So, strong base. Arrhenius defined a strong base as an ionic hydroxide. So, a strong base is something that has a high pH, high conductivity, and according to Arrhenius, it'll produce hydroxide in that first dissociation. So, note that in the previous examples where we had molecular compounds, the molecular compound reacted with water in step 1. Ionic compounds don't react with water in the first step. Ionic compounds dissociate as they've always done. So notice that I've got magnesium hydroxide. Magnesium hydroxide is going to dissociate into magnesium ion and hydroxide ion. This is a strong base according to Arrhenius's modified definition because this hydroxide is produced right away in the first dissociation. A weak base, however, a weak base is considered weak because typically what happens is the base is going to produce the hydroxide in the second step, or if you look at that chemical formula, the base doesn't have a hydroxide attached to a cation. So the example I'm giving you here is ammonia. Ammonia, when it reacts with water, it's molecular, right? So if it's producing basic, that means that this molecular compound must be undergoing hydrolysis. And if it's undergoing hydrolysis, let me change this arrow. If it's undergoing hydrolysis, because it doesn't have a hydroxide in the chemical formula, this is going to be an equilibrium arrow with a less than 50% because it's going to be a weak base. Here, what's going to happen is the hydrogen from the water is going to be donated to the ammonia in order to produce hydroxide, and then we're going to produce ammonium, or conjugate acid, ammonium ion, and it becomes positive because it's accepting a proton. Okay, so this is your proof of your strong or your weak base, and this is your proof of base. Now I'm going to skip over this next example here, only because I want to talk about amphiprotic substances in a subsequent video. I do want to show you this example because there are a couple substances that are going to be neutral regardless of what they are. So NaCl is one of those examples. NaCl, again, it's an ionic compound. We put it into water. It's going to dissociate into your sodium ion and your chloride ion. Typically what's going to happen is your anion is going to undergo hydrolysis. But the problem with chloride is that if your anion undergoes hydrolysis, that's going to be a weaker reaction. Every subsequent reaction that takes place is weaker than the previous reaction. So all of this NaCl is going to dissociate. The chloride would theoretically react with the water in a hydrolysis reaction, and this would be a less than 50% reaction. Because chloride doesn't have hydrogen to donate to the water, it's going to accept a hydrogen from the water, which means it'll produce hydroxide and HCl. This reaction here can't happen. We can't produce a hydroxide ion, which proves base, and a strong acid, because our definition of the strong acid is that 100% or greater than 99% of that strong acid is going to undergo hydrolysis. So it is impossible for this HCl to exist as a molecule in water. It will completely obliterate. And if it obliterates, it would neutralize this OH because the hydronium that it produces would neutralize the hydroxide you're seeing is being produced. So there's no possible way for this reaction to take place, so we can cross it out. NaCl is something that would be neutral. So any of those anions above the gray line, the conjugate base anions, Cl minus, NO3 minus, SO4 2 minus, any of those 6 above the gray line, those cannot undergo hydrolysis, because if they do, they'll produce a hydroxide and a strong acid, which cannot happen. Okay. So that's essentially, I want to leave the rest of it, that's essentially what's happening here. And this is kind of a very quick look into modified Arrhenius. In class, we're going to do a bunch of examples together. I highly, highly, highly recommend that you take a little bit of time here to start yourself a study sheet where you're keeping track of what is important for your solution equations here. I am going to give you just one thing. Ionic compounds dissociate And that means no water in step 1. Okay, so that's important for you guys to realize. The other thing is molecular compounds. For example, acids or other substances that test acidic or basic undergo hydrolysis in step 1. Okay. So that's kind of the first thing that you should go on your study sheet, because this is where you're going to have to start for all of these reactions. So have a look at this. I completely expect questions when you guys come into class. Even if you don't quite know where it is you want to start, with your questions, pick one thing. Just pick one thing. It'll probably get us going on a discussion in class. But there's a lot to chew on here. So make sure you spend a little bit of time here. I will come back and I will talk about amphiprotic and I'll talk about polyprotic substances in another episode. But for now, this is plenty for you guys to think about. So definitely give it some thought. Definitely organize the notes, and we will chat when we get into class. As always, guys, I hope you're doing well, and we will see you very, very soon.